We rely on benchmarks to measure AI capabilities, but even the best benchmarks only give us a narrow glimpse into what AI systems can do. Consider a benchmark. If you have a model that's really bad, then it's going to get 0% on that benchmark. But if you have a model that's really, really bad, then it's also going to get 0%. And there's no signal that we can use to try to compare these two models and say which one is better, even though one is a lot better than the other. In the other case, you might have a model that is really, really good, and that will get 100%. But you might also have a model that's really, really, really good, and that will also get 100%. So there's no signals to compare these two models either. The only case where we can compare these models is when we're in the middle. So the two models are not too good and not too bad. Then we can actually say which one is better or worse. The problem is that this middle regime, where they're not too good or not too bad, is quite a narrow one. Benchmarks saturate really, really quickly because model capabilities are improving so fast. So how can we solve this? Our approach is to use a statistical framework to stitch together different benchmarks, allowing us to compare models across a wide range of capabilities. Our core idea is to assume that each model has its own latent capability, and each benchmark has its own latent difficulty, as well as a slope that tells us how quickly the benchmark gets saturated. Once we have this, we relate benchmark performance to the difference between model capabilities and benchmark difficulties. This follows an S-curve with 3 different regimes. The first regime is when model capabilities are much worse than benchmark difficulties. So you just get 0% on this benchmark, or whatever the random baseline is. The second regime is when you're actually starting to slope up on the S-curve. Here, the model capabilities and the benchmark difficulties are roughly comparable, and they go up at the rates that is determined by the slope parameter. The final regime is when the model capabilities are much better than a benchmark difficulty, and that means that you saturate the benchmark. You get roughly 100%. Now that we have the statistical framework, we can then estimate these model capabilities, benchmark difficulties, as well as the slopes, based on real-world data that we've collected in our benchmarking hub. In total, we include data from several hundred different models, over 40 different benchmarks. This framework assumes that model capabilities can be captured by a single number, which is oversimplified, but encouragingly, it still gives us a lot of useful information. For one, it allows us to compare models across a wide range of different capabilities, even if those models were not evaluated on the same benchmark. And this is really important because it means that we can get a trend in these model capabilities over time. And we can extrapolate this trend to make simple forecasts of how AI capabilities will evolve in the next few years. This trend in model capabilities also allows us to study algorithmic improvements. The idea here is to break down improvements in model capabilities into increases in computational resources, as well as improvements in software. Now, software improvements happen when we have fewer resources needed to get to the same level of capability. And when we study this, what we find is that each year, you need around 2 to 3 times fewer computational resources to get to the same capability score. Now, that's very fast, but some people think things could get way faster still. The idea here is that AIs could recursively improve themselves, getting better and better over a very short time period. Our framework gives one way to try to detect this. If we look at the trend in model capabilities, if we see that there is a change in the slope, this would suggest that there has been a rapid acceleration in model capabilities, perhaps due to this feedback loop. Now, there are several limitations with our approach. For one, because our entire framework is built upon benchmarks, we inherit almost all of their flaws. One example of this is that benchmarks often have models heavily optimized to do well on them, and these models may not perform well in other settings that are not the same as this benchmark. On the other hand, these limitations also provide an avenue for future improvements. For example, right now, our model assumes that all capabilities can be compressed into a single numerical score. But in practice, capabilities depend on more than just one number. They vary across multiple dimensions. So can we extend our framework to account for these? Another avenue for future improvements is to gather data across more benchmarks. This would allow us to construct longer time series, getting data about AI across longer time periods and allowing us to study their implications more rigorously. At the end of the day, our framework is just one particular attempt at trying to stitch together different benchmarks, and it's just an early step. So there's still a lot of low-hanging fruit to be picked. You can see an example of how we apply this framework on our website. where we have a leaderboard showing which models are the best, as well as a graph that shows the trend in model capabilities over time.